All right, welcome back to AP Physics C, Unit Electricity and Magnetism, Unit 2, Conductors, Capacitors, Dielectrics. So here's the second video focused on conductors. In the previous video, we looked at the electric field inside a conductor and around a conductor. Now let's talk about the electric potential in a conductor. So one thing to note is that conductors that are in electrostatic equilibrium, they're what we call equipotential surfaces. What that means is that it's a surface on which all points have the same electric potential. So something to remember, all that, and you remember from the E-field video, all that excess charge is now sitting on the surface, right? There's no electric charge on the inside, which allows us to say that the potential of the conductor is the same throughout. So therefore, the electric potential in or on a conductor is equal to the electric potential at the surface. So want to point out, we forgot to point this out in the last video, the graph, because these graphs will show up a fair amount, right? So this flat portion, this horizontal portion, is what's inside the conductor, right? So it's going to be constant. The second you break the radius of that sphere, then you start following our KQ over R, right? And that's what this breaks down to be, because remember, 1 over 4 pi epsilon naught is our K value. Now, one thing to remember is that in an electric field, the electric field in conductor is always perpendicular to its surface. And one of the main reasons is because it's an equipotential surface. And what that means is that if we move a charge, right, along this surface, we're not doing any work on it. Okay, is one thing. So it's very easy to move it, and because the electric force does no work on a particle moving on the equipotential surface. If you remember the work equation, work equals Q delta V, right? Equipotential surface means this is equal to 0, right? So there's no work being done. So if there's a multiple choice question focusing on that, right, on equipotential lines or equipotential surfaces, there's no work being done. Now, one of the most common questions here for electric potential is the double sphere, or inducing a charge on a second sphere. So a charged conductor can induce, which means give its charge to a non-charged conductor by simply, a couple ways. And the way they like to do it on the AP test is they'll attach a wire from one to the other, okay? And so what happens is charge passes down from sphere A to sphere B, right, until they reach equipotential. So it's going to pass charge passes the charge until they are at the same voltage. It's kind of like how temperature works. All right, so the exchange of energy between a hot and a cold surface will stop once they reach the same temperature. So it's kind of the same thing. So what happens is this will have a voltage, this will have the same voltage over time. And the number that pops out a lot is 10 to the negative 16th. Okay, seconds. That's how long it takes. And so we can almost say that this is simply an instantaneous process, right? Because that's like 10 to the, like a femto picosecond, right? Or something like that, all right? So let's see how this is done in practice, right? So let's look at the double sphere or the connected sphere conductor problem. You'll see the same picture, right? So here we're going to look at what is the ratio of surface charge density from sphere A to sphere B. So what we're doing is we have an isolated spherical conductor, right, of radius A that has charge Q. Okay, a second isolated conductor of radius RB, which tells us that it's half of RA, has no net charge. We then connect a wire between them, and remember in that time, 10 to the negative 16 seconds, the system comes to equilibrium. And they want us to calculate what is the ratio of the surface charge density on sphere A to sphere B. Okay, so let's look at the electric potential equation, V equals KQ over R. And so that allows us to say, we know in that 10 to the negative 16 seconds, we know that V is going to be equal. So K Q A over RA is going to equal K QB over RB, right? And so right here we can automatically cancel out K because that's the same value. So we would have QA over RA equals QB over RB. Now what happens is this charge is going to be different because of the size, right? And the charge is based on this sigma, right? This sigma, this charge density. So it's going to be Q over A, okay? And so A, it's a sphere. And again, on the AP test, they like spheres. The surface area of a sphere is 4 pi r squared, which means the Q that is on each one of these spheres is simply going to be 4 pi r squared sigma. Okay, and so what I'm going to do is I'm going to take that, plug it in here for QA and QB, and then continue to do my algebra. So we're going to have 4 pi RA squared sigma A over RA, and that's going to equal 4 pi RB squared sigma B over RB. Keep doing algebra, right? The 4 pi's would cancel out. This RA cancels one of those up top. This RB cancels one of those up top. And we end up with RA sigma A equals RB sigma B. Well, they tell us right here that RB is 1/2 of RA. So let's plug that in. So I'm going to take that and plug it in there. Or I can go the other way, say that RA is double RB, whichever one you want to use. Okay. So we're going to say RA sigma A equals 1/2 RA sigma B. And what happens? The RA's now cancel out, and we say sigma A is equal to 1/2 sigma B, which then if I solve it for the ratio, so sigma A over sigma B is going to equal 1 over 2. Right? Or you can kind of write it in a relationship here, say that 2 sigma A equals sigma B, right? You can say sigma B is 1/2 sigma A, or sorry, sigma A is 1/2 sigma B. And remember that sigma is charge density, right? And so they're saying that A's charge density is half of B's because it's bigger, right? Go back to the E field video, we talked about the point. Right? Most of the charge is going to be up here at the point, not so much down here where it's the curve is bigger because of that charge density, right? So it's charge per unit area, right? And so for really all this stuff to kind of equalize, you would have to have more charge density in B than you would A because of the size. Okay, so that's conductors. The next set of videos, we're going to focus on capacitors and dielectrics. So a dielectric is just simply a capacitor with an added piece to it. Okay, so you're going to see a lot of the equations, they're going to be the same.